Hello, ladies and gentlemen, coming to you not quite live once again from One Take Studios, where you are going to love today's topic, which is factoring polynomials. But I'm putting advanced on here because these are not your normal factoring techniques for most cases. The first one is probably the most common, so we will start with that, and that is called factoring by grouping. All right, so this one's not super crazy, but the concept is this. If I'm factoring by grouping, usually it means that I have four terms, and that I'm using the distributive property backwards. Ooh, scary. Except that this is actually kind of complete nonsense because technically you can't use a property backwards. All properties go forwards and backwards, so they don't really have a forwards or a backwards. You're just using it the reverse of the way that you usually think of the distributive property. All right, so let's take something apart here and take a look at this. We've got x cubed. Ooh, we do have x squared. That's supposed to be a cube. All right, x cubed minus x squared minus 25x plus 25. All right, so we have four terms, factoring by grouping. Ladies and gentlemen, I don't know if you like Star Trek, but here we go. You have four terms, yes? How does Spock greet people? Live long and prosper. All right, sometimes instead of calling this factoring by grouping, I call it Spock. Because what I'm going to do is take two terms and group those, and examine those two, and then take the second two and group those and examine those two. So even though there's four, we're taking them two and two, just like, whoo, fingers, they can work. There we go, 2 and 2. If I'm looking at these, I'm saying, all right, x cubed, x squared, what do they have in common? They both have factors of x squared, and so what I'd like to do is I'd like to pull out the x squared. If I pull it out, what's going to be left? Well, typically, distributive property, we think we're going to multiply something in to the parentheses. Since we are taking something out, let's see, multiplying goes in, we must be dividing when we pull something out. So x cubed divided by x squared is x. And x squared divided by x squared, well, anything divided by itself is 1. Great. That was so much fun. We should do it again. All right, so let's check out these guys. We've got a negative 25x plus 25, and let's see, common factor, ooh, 25. And you know what? I don't like having a leading negative, so I'm going to pull a negative 25 for reasons that will soon appear hopefully useful to you. Again, if I'm pulling something out, it means that I'm dividing. So negative 25x divided by negative 25 is x. And 25 divided by negative 25 is negative 1. Wait a minute, I've seen something like that before. Huh. Well, this is quite interesting. What do you actually see here? Because this was two terms here, and it had something in common, and we pulled it out. Distributive property. This is two terms, they have something in common, we pulled it out. Do you see the same thing happening here? This is a gigantic term, this is a gigantic term. They have something in common. What if we pulled that out? What if we pulled out the x minus 1, and had something back? So if we pull out the x minus 1 out of here, we divide out the x minus 1, that would leave us with x squared. And if we pulled the x minus 1 out of here, divided it out, that will leave us with a minus 25. Hey, that worked pretty well. Ooh, and bonus, did you see it? Are you used to seeing it? That's a perfect square, that's a perfect square, that's a subtraction sign. That is difference of squares, difference of squares. Know it, love it. I would not include that necessarily in advanced factoring, but it's something you should definitely be aware of, because that means that this can actually break down farther. So x minus 1 is a factor, and then this is going to be x plus 5, and x minus 5. So grand total, if I'm factoring, this is it. I have 3 individual factors for this, which kind of makes sense. If I were to start multiplying this back together, I would expect to see something x cubed. There we go. All right, so factoring by grouping is one thing that you can do. But why stop there? Dun, 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 dun. Ooh, okay. Now, I need you to not panic. I need you to listen. Sum of cubes, a lot of people don't like it. It's okay. You can not like it, but you can still understand this thing. All right, sum of cubes, kind of like here we just said difference of squares. We could recognize it because we were subtracting squares, so difference of squares. Curiously enough, sum of cubes, we are adding cubes, just like it says, sum of cubes, one cube plus another cube. If I see this, there is only one way to take it apart, only one way to break it down into its factors, and that is going to look something like this. A plus b which some people would look at this and go, well, I know, that's going to be a plus b times a plus b times a plus b. No, it's not, because in order to not have a middle term here, we're going to have some positive and negative interaction here so that middle terms drop out. This is going to be a plus b, and a times a squared is a cubed, so that's going to be good. And b times b squared is b cubed, and that's going to be good. And this little guy right here makes it so that if we finish the whole massive distributive property process, all the middle terms will drop out between the positive and the negative that's happening there. So this is the only way to take apart sum of cubes. It is a binomial times a trinomial, and I will tell you right now that this trinomial is prime. That means it will never factor further. So if you can take this apart into these two pieces, those are your factors. You are done. I'll do an example in a second, but while we're on the joy of sum of cubes, there's also difference of cubes, not to be confused with difference of squares. Difference of squares, we're subtracting squares. Difference of cubes, two guesses, you got it. We're subtracting cubes. It looks a lot like sum of cubes, but there's a minus sign. And the factors look a lot like sum of cubes with slightly different signs. A cubed plus b cubed starts off with a plus b as a factor. A cubed minus b cubed starts out with a minus b as a factor. The trinomial, again, very similar. We're just swapping the signs of that middle term to make it happen. Okay? This is what this looks like. This is how we take these apart. Now, I would recommend using these as a model for you. And to show you what I mean by that, our first example here is x cubed plus 4. Now, in order to do this, your brain has to say, hey, that's a perfect cube. I recognize that as a perfect cube. And 64 is also a perfect cube. If your brain is currently saying, yeah, but 64 is a perfect square, it is, but it's also a perfect cube. If you do not know your perfect cubes, you're going to be stumbling over this big time. All right, so take a moment, list the first 5 perfect cubes. Put them down in your notes someplace. 1 cubed is 1, so 1 is a perfect cube. 2 cubed is 8. 8 is a perfect cube. 3 cubed is 27. 27 is a perfect cube. 4 cubed is 64, so 64 is a perfect cube. And 5 cubed is 125. That's a perfect cube. If you can recognize those 5, you're probably going to be fine. All right, so my advice would be view this as you would this. Try to figure out what's being cubed. All right, that's how I'd like to frame it in your brain. Ask yourself what's being cubed. So if I'm looking at this, the x is clearly being cubed. The 64 is not being cubed. The 64 is a cube. So this is 4 cubed. I'm just rewriting this in a slightly different perspective because it allows me to see what my a is and what my b is. That's my a, that's my b. I'm going to follow the model. Wherever I see an a in the model, I'm going to put an x. Wherever I see a b in the model, I'm going to put a 4. So that's going to look something like this, where we've got, instead of a plus b, this will be x plus 4. X plus 4, that kind of ran together a little bit. Sorry about that. I can make it better. All right. And then this says a squared, so this is going to be x squared, minus a times b, so minus x times 4, so minus 4x, and then plus b squared. Remember that 4 is my b, so plus b squared is plus 16. Ladies and gents, those are my factors. A binomial times a trinomial. Again, this last one, you can try all day long. Things that multiply to make 16, add to make negative 4, ain't happening. This is it. You're done. Now, I want to run one more, a little bit excessively different, because, what if there's a number there? A lot of people panic. I'm asking you to not panic. You can do that, right? Not panic? So if we're looking at this, same kind of thing. I need to recognize this is one of my perfect cubes. This is a perfect cube. And oh, by the way, that's a perfect cube. And we're subtracting difference of cubes. I have to recognize it. If I don't recognize it, I get no chance. Ask yourself again, remember the question? What's being cubed? So here, what's being cubed is probably the most challenging part. There is a 5 being cubed and a y being cubed, because 5y cubed would be 125y cubed. Note the parentheses. Minus, what's 8? Well, 8 is 2 cubed. There's my a, there's my b. Use the model. A minus b, 5y minus 2. 5y minus 2 times, okay, we got to be careful. This says a squared. Remember that 5y is my a, so I'm squaring 5y. That means I should have 25, hopefully, y squared, plus a times b, so plus a times b, that's the 5y times the 2. So plus 5y times 2, that's going to be 10y. All right, and then, this is plus b squared. My b is 2, so b squared is going to be 4. If you're ever not sure about that, start multiplying it back together. Make sure it works, because I'm telling you, it does. Now, I'm going to hear something, I'm going to say something that you really don't hear a math teacher saying very often. Once you establish if it's sum of cubes or difference of cubes, after that I want you to ignore the signs. All of the positives and negatives you need are built into these models, all right? Model right here, boom, model right here. All the positives and negatives are built into these guys. So when you look at this 2, you don't need to see it as a negative 2. You need to see it as a 2. The signs will all work out. Just follow the models, okay? Sum of cubes, difference of cubes. It's going to take a little bit for your brain to adjust to that, so please make sure that you write it down someplace where you can find it. Again, put your list of cubes maybe along the side, and that would be helpful as well. All right, now we have my favorite. Of course I have a favorite. All right, so we can factor by grouping, we can do sum of cubes, we can do difference of cubes. Dun dun, what? Factoring by graphing? We can factor by graphing? That's quite interesting. Okay, let's just dive in with a blurry camera image. Come on, guys, you can do this. What if I take this out of the picture? There we go. For some reason that makes it better. All right, I will move those guys out of the way. All right, so let's look at this from a graph perspective. I'm going to pull up this screen here, and that was not the one I was going for. Dudes, give me something good. There we go. There we go. Right here is actually the one I wanted. All right, so this is the equation that I had written on my paper. Sorry, the expression that I had written on my paper, but written as an equation for the purposes of graphing. It was x cubed plus 6x squared plus 3x minus 10. So if I take my expression and I graph it, I set it equal to y and I graph it. What do I see? This one's really nice. My x-axis, they're counting by ones. This crosses the axis at 1. It crosses the axis at -2. It crosses the axis at 3, 4, -5. So I'm going to take a second on my paper, which I'm going to come back to here in a second. I'm going to jot down my x-intercepts. So my x-intercepts, I've just said we've got a -5 sitting here, as well as a -2, and a +1. Why does this matter? Well, jumping back, there's my other screen, right there. Intercepts are zeros. They are things that work as solutions for this, which means if you think about when we actually solve a quadratic, say, by factoring, we take the factors, we set them equal to 0, and we get answers, we get roots. What if we were to take that process and work backwards? Think of it as Jeopardy. These are the answers. What questions did they come from? What factors did they come from? Well, if -5 is going to be one of my answers, that means that x plus 5 would have had to have been a factor. Because if I set this equal to 0, it's -5. So if my x-intercept is at -5, x plus 5 is the factor that would produce that 0. I can do the same thing here. If it's -2, that means I must have had a factor of x plus 2. Because if I set that equal to 0, I get -2. One more, if 1 is going to be my 0, my x-intercept, I'm going to have to do x minus 1 as a factor, because again, that would produce that value right there. Guess what? That's it. If you start multiplying all that back together, you will get x cubed plus 6x squared plus 3x plus 10. That's it. Those are the factors. We're done. And so a lot of people don't really consider graphs as a viable option for factoring, when really they're not bad. Obviously, those were really nice numbers. It came out cleanly, and so that one worked really well. So maybe it's not always the best option, but it works. It takes it apart. All right, so let me throw one monkey wrench in that, and let's look at this one right here. All right, x cubed plus 7x squared plus 5x minus 28. Again, we would probably expect to see 3 intercepts like the last time. It was x cubed, 3 intercepts, x cubed. All right, so I'm going to go back to my graphing screen here and jump over to my second page where I already have it graphed so we can look at it. All right, so here's the thing. The other one crossed really nicely and neatly at -5, -2, and 1. This crosses someplace between 1 and 2. 1, 2, 3, 4. Ooh, it crosses at -4 nicely. Excuse me. But this other crossing point is between -4 and -5, and I'm not exactly sure where that is. I can use my table a little bit to clarify from some stuff. If I go with Control T for table, I can kind of see by looking at this, where was it? We thought that -4 worked. Let's arrow up. Check it out. -4 is one of my zeros. -4, 0 is actually on the x-axis. So I have one really good point, but if I go up one more time here, we can see between -4 and -5, we're not hitting 0 again, and there's clearly something happening there, but it's not nice and neat. What can we do with this knowledge? Well, I'm going to record the one x-intercept that we know is good. We've got an x-intercept here of -4. So, back to our other screen. What might I do with this? I know that this comes apart, but I also know that this can't be the only factor. Work with what you know. If I know one of my factors is going to be x plus 4, right? Same logic as before. I know that x plus 4, based on this, is a factor. If I could remove that factor from my polynomial, if I could take it out, pull it out, divide it out, what would be left would be my other factor or factors, depending on the problem. How do I pull this out? Division. I want to divide this factor. I want to separate it from the rest of the polynomial. I don't know about you. I'm not using long division here. I'm going to use synthetic. If you are not familiar with synthetic, probably go seek another source. But I'm going to go with -4 is my number here. My coefficients are 1 and 7 and 5 and -28. 3, 2, descending order, no gaps. We are good. Okay. My addition line, first number drops down. That's going to be a 1. 1 times -4 is -4. Let me add. That's going to be 3. 3 times -4 is -12. Let's see, that's going to be -7. Interesting. -7 times -4 is +28. Look at that. We should be really, really happy to see that. That's the remainder. The remainder is 0, which is what we thought was going to happen anyways. That means it goes in evenly. This is a factor. And what's left is the other factor. So x plus 4, I know that that works, x plus 4. And remember, this is my depressed expression here. If this was x cubed and I divided, this is 1x squared plus 3x minus 7. 1x squared plus 3x minus 7. Things that multiply to make -7 and add to make 3. That's not going to happen. This factor does not break down further. Therefore, this is it. This is it right here. If you were looking at this one saying, well, hey, this has 4 terms. Couldn't we use factoring by grouping? Couldn't we use Spock to make that happen and just kind of start grouping them and everything? That doesn't work for every polynomial. So in this case, you would have no success trying to factor by grouping. But factoring using our graph and a little bit of division, yay, happiness and joy. We got this, all right? I think the biggest thing with factoring is that there are so many things to keep track of because there's lots of different ways to factor. And you can't just pick one. You have to be fluent in multiple factoring methods. Okay? So keep your notes nearby, use them as you practice, and just keep trying. All right? Thanks. Bye.